congrats to all of you for surviving this conference. Yeah. Yeah. You're only an hour and a half away from the end of the conference. By the way, stop me when I'm going over time because I have 40 minutes worth of slides. So LCS, or longest common subsequence. The input is two sequences of length capital N. And we're looking for the longest common subsequence. It doesn't have to be consecutive. There's dynamic programming that we like to teach in our undergrad algorithms class. It takes approximately n squared time and I think linear space. And you can do a little bit better, but it's a long-standing open problem whether we can get substantially faster than n squared. So, I mean, there was a long-standing open problems until this fine-grained explosion for the past few years. And now we know that assuming this strong ETH hypothesis, you really need approximately n squared time. And this is a very exciting result, very celebrated. It's a sequence of results. I think all these coverage was for the second one, BI15. That was actually 8 distance, but doesn't matter. What I want to show you is some fine-grained print on this result. This is only for exact LCS, whereas all of this excitement was about applications to biology, where what we really care about is approximation. So this is, as far as I can tell, this is the most exciting question we should all be working on, or at least I should. Are there fast approximation algorithms for longest common subsequence? So we haven't solved it yet. It's still an open problem. I want to share with you some of the recent thoughts about it. But first, let me start with some ancient history from 2 years ago on how to get the exact harness. So the strong exponential time hypothesis postulates that if you have a k-set, solving k-set requires approximately 2 to the n time. So here's the reduction. We start with a CNF phi, and then we construct a gadget for every half assignment. So you can look at all the assignments to the first n/2 variables, and for each alpha, we construct a gadget AF alpha. And similarly, you can construct a gadget for each of the half assignments to the last half of the variables. And the gadgets have this property that the LCS of A and B is large if and only if the half assignments together generally satisfy the original formula. And now we want to concatenate all those gadgets. So we're just going to write all the, so this is a CNF with 4 variables. And these are all, on the top, I have all the gadgets for my first string is all the gadgets for the first 2 variables. And on the bottom, I have all the gadgets for the second 2 variables, for the last 2 variables. And if I have a satisfying assignment, anyway, if I have a satisfying assignment, then 1, 0, 0, 0 is a satisfying assignment. Then the LCS of A of 1, 0 and B of 0, 0 is going to be large. And then we have to match the entire 2 strings, so we're just going to have some other stuff in the reduction that I'm hiding. We're going to match you have like trivial matches that don't get you very much contribution to the LCS. The most important and exciting thing about this reduction is the size. So the size of the reduction is capital N, which is approximately 2 to the n/2. And when you plug back to Seth, then you get the conjectured lower bound on the running time, which is approximately n squared. Questions on this ancient reduction? Okay, good. So what about harness of approximation? So there are 2 main obstacles. And the first one is all these redundant matches that we didn't want, that don't correspond to a satisfying assignment. So yeah, I mean, if I want to approximate the size of the LCS, I can just approximate the number of satisfying assignments, and that's pretty easy to check, and you just sample some assignment, right? So the exciting breakthrough from last LCS by Wood and Buckers ask, what if you want a deterministic algorithm? Maybe we can at least rule out deterministic approximation algorithms for LCS, and that will tell us at least what the randomized approximation algorithm should look like. So, okay, if you start from making an assumptions about KCNF, even for the deterministic algorithm, approximating the number of satisfying assignments is pretty easy. But and maybe it's true in general. Maybe there's some kind of a fine grain P equals BPP, which is true. So that's very plausible. But if you want to have provable guarantees, it's really hard to prove that you can de-randomize some of those questions, even for a very simple class of circuits. So before I talk about circuit classes, let's take a quick trip to the complexity zoo. So the class E is the problems that can be solved in deterministic time 2 to the n approximately. And then we have this e to the np, which is a little bit bigger. Then there's a class of circuits, NC1, which just log depth and poly size. And there's valiant series parallel circuits. Don't worry, we won't need the definition. There are consequences you might hope to prove. For example, you might hope to prove consequence 1, which is that e to the np does not have linear size NC1 circuits. Another consequence which you might want to prove is that this linear size VSP circuits cannot be, it cannot represent all of e to the np. This is a picture I want you to remember from this trip to the zoo. But yeah, there are also two consequences and they're incomparable. Anyway, so the theorem from last ITCS was that if you had a deterministic approximation algorithm for LCS, then consequence 2. And the approximation there has to be very good. So almost, I mean, not quite exact, but very, very good. And our main result, really our only result, is that even if you had any approximation algorithm, so any factor, a constant, or actually even some super constant factors, then you'd actually get both consequence 1 and consequence 2. So a little bit stronger on the consequences, but the main difference I want you to focus on is now it works for, now it's really hard to approximate deterministically. Okay. Questions on the result? Oh, sorry. So this is consequence 1 and consequence 2. I understand that I'm not an expert, but my understanding is we believe both are true, but both are probably hard to prove. So if you prove that your algorithm approximates LCS in deterministic time, then you're doing something exciting. Yeah.
So just to orient in terms of direction. So it seemed like before you were talking about this problem sort of being hard in the sense that if you assume strong ETH, then you can't do this. But now it seems like you're saying if you can do this, then you could prove a lower bound. So it's
Thanks, excellent question. So there is sort of this algorithms imply lower bound framework, where if you can do certain things faster, as far as I understand, if you do certain things faster, then you can have better diagonalization. That's a very not unfair idea, but roughly that's the intuition why this. Yeah. Anyway, so you can prove.
Should I think of this as related to the?
Oh, how does this compare to Seth? So my understanding on Seth is that some people believe it, and so okay. My understanding about Seth is that some people don't believe it and some people are skeptics. My understanding on these consequences is everyone believes they're true, so no one believes that the what we'll be falsifying is actually. It wouldn't be surprising that either of those consequences is true, but it would be very surprising that we managed to finally prove it. So that's okay, and yeah, I think if there are more questions about the result, I'm happy to take them.
I guess one of the conceptual differences is that if you have a faster algorithm for if you disprove the strong ETH, then you get faster algorithms for other things. Maybe it works both ways. If you have faster algorithms for other things, you have faster algorithms for KSAT. Whereas here, it's not going to work both ways.
Yeah, and another interpretation that I've seen is, if you disprove strong ETH and you have a slightly faster algorithm for SAT, who cares? But here you manage to prove circular lower bounds. Okay, unless there are more questions about this, I want to tell you a little bit about this distributed PCP technique, which is just recycled slides from Fox. But I want to apologize. Greg promised you tropical tensors, which is an exciting new problem introduced in the paper, and I'm sorry I forgot to include it in the slides. It also doesn't correlate very well with the weather outside. So, okay, so let me tell you a little bit about this distributed PCP stuff. At least I'm excited. So here's a recap of this old ancient reduction. We have all those we have those like 2 to the n over 2 gadgets, right? And we have this Seth assumption. And for the rest of the talk, you can think of actually working with strong ETH. It's sort of equivalent to the circuit stuff. Okay, and I want to zoom in on this if like LCS of A and B is large, if and only if they jointly satisfy the assignment. And our goal for the rest of the talk will be to obtain a large gap. So previously, if they jointly satisfy the assignment, there was a tiny gap, and we want to make it a huge gap compared to like if they jointly satisfy the assignment, they had a slightly longer LCS than otherwise, but now we want to make a big difference. In other words, we want to amplify the gap. And what's our main tool for gap amplification? PCP, great. Okay, so PCP theorem, right? So there are 2 ways you can look at the PCP theorem. One is PCP stands for probabilistically checkable proofs. Sorry, I can't pronounce that. So you have a CNF and you have a satisfying assignment, and you construct a proof that proves that your assignment is actually satisfying, and the verifier only needs to read this assignment at a few locations. Okay. Another equivalent way of looking at the PCP is this hardness of approximation. That's how I usually think about it. So you have this 3-set phi and n variables, and you convert it to a 3-set phi prime, where approximating phi prime is as hard as solving phi exactly. Okay, and these are equivalent. It takes some time, but when you see it, it's pretty. In hindsight, it's pretty easy. And I want to focus on the second definition. And in particular, I want to focus on this transition from n variables to n prime variables. So this is something I call the PCP blowup, and that's the second. I promise you 2 obstacles, and one we overcome with this cheat of we're only doing deterministic algorithms. But this obstacle we really, in some cases, know how to overcome. But let me tell you what the obstacle is first. So here's like there's a question of what's n prime, the size of the new CNF that I'm constructing. So the original PCP theorem gave something that was approximately quadratic. Polish equivalent improved to near linear. And Dinur in 2007 gave her PCPs quasi-linear. And there is this conjecture slash fantasy that one day we can get a truly linear PCP. So something with like 10n, n prime equals 10n or some. A million times n would also be exciting. But what happens when we compose this PCP with our strong exponential time hypothesis, like the reduction, the old reduction? So the reduction size is capital N, which is I have to enumerate over all the half assignments to the new CNF that I constructed. So even if I had this fantasy PCP, I have 2 to the n prime over 2 half assignments, so the reduction size is 2 to the 5n. And now, if my algorithm runs in subquadratic time in capital N, it's like 2 to the 5.5n, refutes the nothing hypothesis. So not very helpful. Okay. So here's, how much time do I have, Craig? Okay, anyway, I have half an hour, that's fine. Okay. Yeah, okay, great. I like this. Feel free to stop and ask more questions, by the way. Okay, so is, yeah. So is the obstacle clear? Is the problem? Does it make sense? Why? Yeah, right. If I blow up the CNF even a little bit, then it's a huge blow up in terms of the reduction size. So the way we overcome this is something that we call the distributed PCP. But before I tell you about distributed PCP, let me tell you about distributed error correcting encoding. So Alice has half a message, and Bob has a second half of the message. So I have some message X that I want to encode on, it's in bits, and I give each of Alice and Bob half the message. And they each locally, without talking to each other, encode their own half. And now, if I just write the two encodings next to each other, together it's a pretty good encoding of the original message, alpha comma beta. Okay, and I want to do the same thing for PCPs. So let me just recap the first definition of PCPs. So I have this satisfying assignment to phi, and I want to prove to you that it's really satisfying the formula. Okay, so now there is this 3-set phi over n variables that everybody knows, and I give Alice half an assignment, and I give Bob half an assignment. And now Alice writes some kind of a local PCP, and Bob writes some kind of a local PCP. And now I want this, when I take the two proofs and put them next to each other, together I want that to be a pretty good proof for the statement alpha beta, the joint assignment, satisfies the CNF. Now, why do I want this? The cool observation is that this completely circumvents this PCP blow-up, the obstacle number 2. Okay, so here's what the reduction looks like now. I start with this CNF, and I construct a gadget. Instead of constructing a gadget for each half assignment, I construct a gadget for the local proof for each half assignment. Okay, and now the LCS of between the gadgets is approximately the probability that the verifier accepts this proof. So because there is a gap in the probability that the verifier accepts a correct proof versus a corrupted proof, there is now a big gap between the LCS of a good pair and LCS of a bad pair of gadgets. So these proofs are maybe a little bit longer, right? There is some PCP blow-up, but the number of gadgets only depends on the number of half assignments to the original formula. So the number of gadgets, which is the main blow-up, stays the same. Okay, and now there's this question of whether we can construct distributed PCPs. So you can't. There's a quick reduction from set disjointness. So let's look at this. It's actually a 2-set formula, very easy to satisfy, right? I'm going to put node to everything. But so if this is my CNF and not alpha I or not beta I, under what conditions on the vector alpha and beta is this CNF satisfied? Hint, the answer is on the slide. So if you look at alpha and beta as sets, then they have to be disjoint to satisfy this CNF. Okay, and now if I had a distributed PCP, then Alice and Bob can simulate the verifier and find out whether their sets are disjoint or not. But that would break the communication complexity lower bounds for set disjointness. So what we can resort to is Marilyn, Arthur, Bob communication, where Marilyn knows everything, but we don't trust him. So there's this protocol where Marilyn sends approximately root n bits to Alice, and then there are also toss some coins. And then Bob sends a message. Everything is sublinear. That's the important thing. And then Alice accepts or rejects. So this circumvents this lower bound for set disjointness, and we can construct a PCP this way. So again, Alice and Bob have each have half an assignment, but now they also get this hint from Marilyn. And Alice's local PCP can depend on this non-deterministic hint from Marilyn. And this is the verifier. So the verifier reads one large symbol from the joint proof, and outputs accept or reject. So this is almost like this distributed PCP, which I promised you would overcome this obstacle number 2 and get everything that we want. And actually, I'm almost done. Actually, for this work, it turned out we needed to use, instead of Marilyn Arthur protocol, where Marilyn just sends one message, we need the IP protocol, so interactive protocol. Marilyn and Alice talk for a while, and then they send. Then Bob sends one bit, and yeah. So let me wrap up with this summary slide. Thanks for saying, and please let me know if you have any thoughts about this question. So about a little over more than a year ago, some time ago, I met Emil and asked him what's the everyone keeps talking about harness approximation for finding complexity. What's the question? He said, oh, there's this LCS question. And then I thought about it for a while. I met him several months ago. Several months later, still over a year ago, and I started telling him, I have this idea for an algorithm, but he said, no, forget about it. Let's prove harness. And now more than a year later, I'm starting to realize why he said forget about it. So the algorithms, it seems harder than I thought at first, but also the harness. So it's exciting. It's one of those questions where I really don't know. Sometimes you prove harness just for fun, right? Most of the time, that's right. It does. It does. I didn't want to, we just wrote constant because it's easier to write. But it's like near polynomial factors or something. Something large. Yeah. Thanks. It's okay.